Okay, in our previous videos, we looked at carboxylic acids. We saw how we could prepare carboxylic acids, and we saw the reactions we could do with carboxylic acids. However, today what I want to do is change gears a little bit and talk about carboxylic acid derivatives. And the best way to explain a carboxylic acid derivative is to compare them to carboxylic acids themselves. So let's take a look at a generic carboxylic acid. And if we look at the central carbonyl carbon, we can find its oxidation state. And in this case, this carbon has an oxidation state of +3. Carboxylic acid derivatives are similar in that they also have a oxidation state of +3. And usually what they have is an electron withdrawing group coming off the end, with one exception, and that is nitriles, which we'll talk about in a second. If we have an electron withdrawing group, these carbons at the center will also have a +3 oxidation state. So let's take a look at some examples, and then we'll talk about how to name all of these different functional groups and systematically come up with IUPAC names. All right, so the first example is when we have a halogen coming off the end. This halogen is electron withdrawing, and normally we just use an X placeholder for any halogen, but normally what we'll use is something that has a chlorine or a bromine in that position. These are called acyl or acid halides. It depends which textbook you use, but if you recall, this was the reagent we used in the Friedel-Crafts acylation reaction. It was what coordinated with our aluminum Lewis acid, right? All right, so this is an example of a compound where we've got a +3 oxidation state for that carbonyl carbon. All right, let's take a look at some other ones. The next one is fairly similar, where this time this entire group over here is acting as your electron withdrawing group, but same idea. It's electron withdrawing, which means that we've got a +3 oxidation state. If you remember, these are called anhydrides. These can also be used in Friedel-Crafts reactions. However, our textbook has a preference for using acid halides like shown above. All right, the next one that again has an electron withdrawing group, something like this, where we have an ester. And just like in the above examples, we have a +3 oxidation state. Furthermore, we can have nitrogen derivatives. So what if we have some sort of nitrogen group coming off the edge here? This could be attached to carbons or hydrogens off of the nitrogen. That's what these squiggly lines are. It just means it's attached to something. And these would just be called amides. And with amides, we still have this electron withdrawing group, which means that the carbonyl carbon is still going to be a +3 oxidation state. All right, the last one that looks a little bit different than all of the ones above it are nitriles. And with nitriles, we don't really have a CO double bond anymore. However, we still have an electron withdrawing group attached to a carbon. If you go ahead and find the oxidation state of the central carbon, it's still going to be +3, which is why it's thrown in with all of these other carbonyl compounds. And these are just referred to as nitriles. So the rest of this chapter, what we're really going to look at is the reactivity of all of these carboxylic acid derivatives. And it's pretty interesting when we get into it, but before we do that, let's talk about how to name all of these according to IUPAC rules. All right, so the first one that I want to look at is with acid or acyl halides. And it's pretty straightforward. First thing I do is I change the ic acid from the carboxylic acid to a Weil chloride or bromide. And so let's do a compare and contrast here. So the first one I want to do is draw the carboxylic acid. And in this case, we've got a backbone that is 1, 2, 3, 4, 5, 6 carbons long. So it would be a hexane to indicate that we've got 6 carbons. But if you remember, because it's carboxylic acid, we would go with oic acid to indicate that it's carboxylic acid. All right, so then the question is, well, what would it be called if we swapped off that OH group on the end for something like a chlorine? Well, we would also have to change the suffix, right? So in this case, what we're going to do is we're actually just going to target this ic in the acid portion, and we're going to swap it out. So let's go ahead and change this. We've got hex an, but we're going to keep the first O, and then we're going to change the last part to YL, and then chloride. So really all we've done is we've changed our suffixes here. So it's an important switch. The one thing that always throws people off though is you do keep this O here, right? The only thing we're changing is the ic portion, meaning the IC. All right, so let's try another example. Let's say we have this carboxylic acid. This is not usually called ethanoic acid. That just sounds kind of funny. Instead, people just call this acetic acid. And again, we're going to do a switch. And in this case, I'm going to swap out the OH group for a Cl. And we're going to change the suffix around just like we did in the above example. And we're going to keep the parent root, but we're going to add on the YL and the chloride. So in this case, the compound that we have shown above would be called acetyl chloride. So all we want to do is change that suffix. All right, if you have a bromine exchange, all you need to do is swap out this chloride for a bromide, and then you'll be identifying that acid halide. So pretty simple. We normally don't run into acid iodides or acid fluorides. They're not quite stable. And acid fluorides, I don't even know if I've seen one of those. So normally we'll just run into the chlorides and bromides. All right, so let's do the next one. The next ones are anhydrides. And these ones I think are even easier. So with anhydrides, all you're going to do is chop off the acid part of the carboxylic acid and just change it to an anhydride. So really straightforward. So for example, let's say I've got acetic acid and to make an anhydride, we're going to just mush two of these together. So I'm actually going to draw it like this, and I'm just going to say acetic acid times 2, right? Both of these compounds are acetic acid. So I've got two of these, and I'm going to mush them together into one linked system. So in this case, you can kind of see that I've got an acetic acid type group over here, and I've got an acetic acid group over there. Let me change the colors so we can see this more clearly. So it's basically two of these pushed together. But like I said, in order to name it, all we're going to do is drop the acid and change it to anhydride. That implies that two acetic acids were used to make this anhydride. In this case, it's called a symmetrical anhydride because both halves are equivalent to one another, right? There's a plane of symmetry where the left-hand side's the same as the right-hand side. But then the question is, well, what happens if we don't have a symmetric anhydride? And let's take a look at an example. So let's say we make an anhydride that's kind of a combo of this acid and this acid. Well, the acid on the left is benzoic acid, and the one on the right is acetic acid. So if we mush this together, we should get an anhydride that's a combo of both of them. So let's say on the left-hand side, it more looks like the benzoic acid, but on the right-hand side, it looks more like acetic acid. So what I mean by that is we've got this benzoic acid half right here, and then we've got this acetic acid half over here. So we've, again, comboed them together. All right, same idea. We need to drop the acid part, but now we need to combine the benzoic and the acetic part together. However, we need to alphabetize them. So what we're going to do is we're going to put acetic first because it's lower in the alphabet. And we'd say that this is acetic space benzoic anhydride. Let me zoom out a bit. And there we go. I'm not really going to get into some of the really weird examples where you've got, let's say, branching coming off of one or the other. We're just going to stick with naming really simple anhydrides in this course. All right, so the next one we need to look at are esters. And esters, in my opinion, are one of the more complicated ones to name because there's a few new parts. And I think the best way to show this is through an example situation. And let's take a look at this compound right here. You can see in the listing above, we need to change the ic acid suffix to something more complicated. The first thing we need to do is identify the group that is attached to the oxygen. So in this case, this group is going to be called ethyl. So that's going to be listed first. And then after that, it's important to note that we need to have a space. So it's going to actually have a space between the group attached to the oxygen and then the parent. All right, so in this case, we've got this parent over here. And if we think about this as a carboxylic acid, it would look like this part, right? So this would be acetic acid. But what we need to do is we need to drop the ic and the acid and change it to an 8 suffix. And what this really means is we're going to drop off this proton here. So this proton coming off the end is going to be removed, and we're going to essentially name it as a carboxylate salt, which is why it gets that 8 suffix. So we're going to change this to acetate. All right, so we've identified the two key parts of this, right? So now when we go ahead and we name it, we first want to name the group attached to the oxygen, which in this case is going to be ethyl. And then we want a space. And then we want to add in the carboxylate salt at the end. So we'll add this back in, and we'll say that this is ethyl acetate. All right, so like you can see, this is a lot more involved than the other ones, but once you get used to it, it makes a bit more sense. All right, let's try another one. And this one is actually going to be an example from lab. So for example, in the lab video, we created this compound where we had a nitro group coming off of an aromatic ring, and we had an ester. All right, so when we first look at this, I always identify the group attached to the oxygen. In this case, this is a methyl group. And then over here, I would say, well, let's identify this as a carboxylic acid, and name that, and then we'll change it to the carboxylate salt. So if this were a carboxylic acid and we drop that methyl group, it would look like this, right? And if we were to name this carboxylic acid, this would be 3-nitrobenzoic acid. You could also call it meta-nitrobenzoic acid if you want. Really, either option is fine. All right, so just like before, we want to get rid of this hydrogen. So I'll just write, all right, minus H+, and we'll consider the carboxylate salt, where we've got a negative charge on that oxygen rather than a proton. Just like before, we want to drop the ic and the acid, and we want to change it to 8. So this would be 3-nitrobenzoate. All right, so now we're ready to go. What I want to do first is I want to add in this group at the beginning. So this would just be called methyl. and then we want a space, and then down here we want to take this part and add it in as our parent. So this would be methyl 3-nitro benzoate. And this would be the name of the compound that we made during our multi-week synthesis. All right, so these are a little tricky. Make sure you go through the book problems and practice them. It's really easy to flip-flop the naming, especially for esters, so these take a little bit of time to practice with. All right, let's take a look at amides next. And amides are, in my opinion, easier. Again, all we're going to do is drop the ic acid suffix and change it to an amide. So let's go ahead and take a look at a simple example. So just like we saw before, this would be acetic acid. We're going to drop the ic and the acid. And in this case, we're going to change it to just a really simple amine where we have an NH2 group. So we would keep the prefix, the ACET prefix, but now we would add the suffix amide on the end. There isn't any space. This is attached to the parent root. So pretty straightforward. This would just be called acetamide. All right, let's take a look though, because there are amides that are a bit more complicated. So let's say again, we've got acetic acid, but this time we don't have an NH2 group on here. Rather, we've got a methyl group coming off the end. So again, we're going from a carboxylic acid to an amide. The parent carboxylic acid is called acetic acid. We've got this ic acid that we know we need to drop. But this time, just like with esters, we need to identify the group coming off of the nitrogen. So the group coming off of the nitrogen is a methyl group. So what we're going to do is we're going to add that at the beginning, but to indicate that it's coming off of nitrogen and not something else, we're going to say N-methyl. And the N needs to be capitalized in this case. So we'll go ahead and indicate that substituent, and then we'll just identify the parent as normal. So it'd be N-methyl acetamide. So let's make a note for this, and we'll just say note, label nitrogen substituents with N-group prefix. So pretty straightforward, kind of like esters. The only difference is you have to add this capital N before to indicate that the group is coming off the nitrogen, not somewhere else in your molecule. It's less ambiguous that way. All right, let's do one last one. This last one's a bit more challenging. I'm going to use a different acid this time. And if you remember, this is called formic acid. Formic acid is kind of half aldehyde, half acid, but because carboxylic acids have a higher priority for naming, that's what gets the substituent, or the suffix label here. All right, and let's compare this to an amide, where in this case, we're going to have 2 methyl groups coming off of it. Well, we need to label both of these methyl groups. So what we're going to do is we're going to do N, N dash dimethyl. It's almost like when we label methyl groups off of a long alkane. If we have 2 methyl groups coming off the same carbon, you have to give the number of the carbon twice, right? In the same way here, you have to list the nitrogen twice to indicate that the methyl groups are coming off of that exact same nitrogen. So both nitrogens are capitalized as capital N's. So we've got NN dimethyl, and then it would be acetamide. And there we go. All right, this is actually a pretty common solvent in organic chemistry. This is referred to as DMF, And as you can see, this is a mouthful, so it's just easier to abbreviate it. Oh, holy cow, this should be formamide. I was just getting stuck on the acetate or acetic acid as being our parent acid. So in this case, we do want to keep the form group as our parent, and then we're just going to swap out that ic acid. So this would be dimethyl NN-dimethyl formamide. All right, like I said, I want you to know the basics of these naming systems, meaning what suffix to use, how to convert from a carboxylic acid to some sort of carboxylic acid derivative, but I'm not going to really push the envelope in terms of wacky branching and, well, what happens if we have, let's say, branching off of this versus this. We're not going to get into that. We're just going to keep it at the basics for right now. All right, good luck studying.